Hello and welcome to this Getting Started with Easy5 for Adams users video. This video is intended to give you an introduction to the MSc Easy5 product, but particularly focused on introducing Easy5 to those of you who are already experienced Adams users. However, having said that, I'm sure for those of you who are not familiar with Adams, you will still learn a lot about Easy5 nonetheless, although some of the bits where we explore the Adams model and the integration between Easy5 and Adams might be new to you. So let me give you an overview of the ground that we're going to be covering in this video. And firstly, I'm going to just explain a little bit about the goal of this Getting Started guide, why we're doing what we're doing here. Then I'm going to give you a brief introduction to Easy5, just a couple of slides on the history and what exactly Easy5 is. And then we're going to spend the bulk of our time looking at the modeling of a simple mass spring damper system. Now, if you are an Adams user, this might appear to be a very simple model, and it is. And to anyone who's done engineering physics or dynamics at university level, you should be fairly familiar with the concept of the single mass spring damper system. But what we're going to do in this video is we're going to look at how to replicate the dynamics of this system using firstly the Easy5 block diagram approach, which simply models the mathematical equations directly in Easy5. We're then going to look at how to do the same thing using a transfer function, and this is particularly important for mechanical engineers to be able to talk to and relate to electronic engineers or control system engineers who make extensive use of transfer functions. Then we're going to look at the Easy5 single mass spring damper component, which is an engineering component that has all the mathematics built into it in order to be able to model the system. And then lastly, we're going to look at how to couple Easy5 with Adams and run Adams and Easy5 in co-simulation mode using the Adams mechanism extension. We're then going to look at including nonlinear physics into the problem. We're going to add some friction to the model. We're going to add contact between the mass and the bump stops, and so we'll be looking at adding a contact or impact statements into that. And then lastly, we're going to look at how to add a PID control system to our model so that we are able to actually control the position of the mass using a control system in Easy5. So that's where we're going. So let me just say a few words about the goal of this Getting Started guide. It's certainly not meant to be a comprehensive overview of everything that is available in Easy5. It's really just a video to get you started, and I hope it'll whet your appetite and you'll be keen to install Easy5 if you haven't done so already, particularly if you are on the MSc1 licensing system. It's already available to you. So get it installed, get playing with it, and I'm sure you will soon benefit from being able to use Easy5 as another very powerful tool in your toolbox as an engineer. So let's move on then and just give you a brief history of Easy5. So Easy5 development started in 1975, and for the first 10 or 11 years, it was a product, an in-house product developed by Boeing. It was being used by Boeing's mechanical engineers, system engineers, engineers looking at flight control dynamics, looking at mechanical system performance, looking at hydraulics, looking at gas dynamics. And so this was primarily an in-house tool developed by Boeing and for Boeing engineers. Boeing then commercialized this tool in 1986 and started to sell it more widely, and so it was sold to many engineering companies around the world, many of whom were Boeing partners who then were able to develop subsystems that interfaced with the Boeing models, but also many other companies acquired Easy5 and used it simply as a mathematical modeling tool for their engineering systems. And then in 2002, the product was bought by MSC Software, who took over then the development and the support and the training of Easy5. And so it became Easy5 and has continued up until today as an MSC product. Just a little bit about Easy5. Easy5 is a block diagram based tool for system level simulation. So what that means is that the physical equations governing the systems that you are trying to model are then being represented by mathematical blocks, and each block will take time varying information from other blocks, and it will calculate new information to pass on to other blocks or to generate as system outputs. And so basically your job is to reduce your system to the necessary components or blocks that capture the physics of the problem, and then you can run steady state, you can run transient dynamic simulations on the model, and very early in the development stage, you can get a very good idea of the dynamics and the performance of the system. So one of the really powerful things about Easy5 is that it allows you to model complex multidisciplinary systems in one model, in one simulation. And so Easy5 has a whole host of engineering libraries that allows you to model hydraulic systems, control systems, pneumatic systems, things like fuel systems, mechanical components, flight dynamics, thermal systems, gearboxes, clutches, electrical systems. It can even handle complex multi-phase fluid modeling. And so these libraries contain many, many years of extensive research and experience in these various disciplines. And Easy5 is a tool that allows you to pull the necessary blocks from these libraries to put them together into a system level simulation that captures the behavior of your system. And the great thing about these libraries is obviously the mathematics behind each of these components has been extensively tested. It's well documented. And so you are then able as an engineer to use these quite complex models in some of the blocks with confidence, knowing that it's capturing the physics of that specific component or subsystem very accurately. So we're going to move on now and just discuss basically the model that we're going to be looking at today, which is a simple mass spring damper system. And so what you see is we have this yellow block, which is a mass of 50 kilograms. We have an external force applied to the block on this side. We have a spring and a damper. Now, if you're familiar with Adams, you'll know normally that Adams combines the spring and the damper together. I've just separated them out so that we can see them more clearly. We've then also got some bump stops in the model so that if the block moves too far, it'll make contact on either end with these bump stops. We can include friction between the block and the ground, and we'll do that a little bit later. We've got a little position indicator just showing us the movement of the block as a function of time. So what I'm going to do is just move over quickly to the Adams model and just show you that there's nothing fancy going on in the Adams model. It's just simply a very simple Adams model. Let me show you all the nuts and bolts behind the scenes here. So if you look at the tree structure, we've simply got the mass and the base. I could have made the base part of ground, but I've simply made it an extra part, which I've locked to ground. In the background here, you can see the joint that locks the base to ground. The joint that connects the yellow block to the base is simply a translational joint. So I've just got a translational joint over there, which allows movement in only one degree of freedom. Here you can see the external force that is applied to the block. I've got the standard Adams spring and then a damper over here. And that's essentially the simple version of the model. Later on, we're going to include joint friction. And so you know that you can add friction to any translational joint. And we're going to look at that a little bit later. And then what I've also done is I've modeled 3D contact on this side over here between the yellow block and this bump stop over here, and I've modeled contact on this end as well. And so that's the model. So let me just deactivate the contact for now so that we can simplify the model up front, and we'll add some of these things a little bit later. So I deactivate both the contacts, and I'm going to deactivate the friction force. And so we then have really the most simple mathematical model here of a moving mass restrained by a spring and a damper. So let's start by just quickly running a simulation. I'm going to start the simulation with a force of 20 newtons applied to this block. So it's modeled in equilibrium, and all we do now is we simply start a simulation. Let's just run it for 30 seconds and see how the model responds to that step input of 20 newtons. And you can see that the mass moves up to a point, it kind of oscillates around a new equilibrium point, and because there's damping in the system, it slowly damps itself to a steady state position. What we can also do at this point, it takes about 15 seconds to kind of settle. So let's just make the model a little bit more interesting. I'm going to go and change the force, and I'm going to bring up the function builder, and let's just do a little step function here. So we're going to do step as a function of time, and we're going to say, right, for the first second or so, the value is 0, and then at 1.1 second, the value steps up to 20 newtons, and then we're going to add another step function of time, and what we're going to do is we're going to say, right, after 15 seconds, we're going to step the force down back to 0 again. So I'm going to do minus 20. Just to check that we are doing the right thing. We can see there's our step function stepping up after 1 second to 20 newtons, after 50 seconds stepping back down to 0. So we're going to change that, and let's apply that to the model and give it a run. All right, so the force steps in, oscillates for a few seconds as it starts to settle. And then if you're watching the time up here at 15 seconds, the force will switch off and the box will return back to its equilibrium position. All right, so there the force is switched off, and so it actually overshoots quite far past the 0 position, and in a typical underdamped system behavior, it's now oscillating around its final settling point with the relatively low damping value that we've used in the model. So that's it. There's really not much more to the Adams model, fairly straightforward and simple for anyone familiar with Adams. Just to give you an idea of what this box looks like, we can simply go to the mass, and let's just do a measure, and let's just measure the mass center of gravity position in the x direction, and we can see the typical response we would expect, an overshoot, settling down, and then as the force switches off, it returns and settles in this direction. All right, so let's return to the presentation. So let's look at the mathematical equations that are behind the modeling of this mass spring damper system. And there you'll see the diagram of the Adams model. We've got the mass M, we've got the spring with the stiffness K, we've got the damper with the damping coefficient C, and we want to track the displacement, the velocity, and the acceleration of the block in the x direction. And so we know that Newton's law says that the sum of the forces equals mass times acceleration. So what are the forces? Well, we've got the external force that's applied, and then in the opposite direction, so minus the damping force and the spring force gives us a resultant force which equals the mass times the acceleration. So we've got Fk, which is our spring force. That's the spring stiffness times the displacement of the spring. And we've got the damping force, which is the damping coefficient times the velocity of the block. Now, if we rewrite this equation in terms of acceleration, then we simply get 1 over the mass times the sum of the forces. And so we've got the external force minus the damping coefficient times the velocity minus the spring stiffness times the displacement. Now, this equation can be represented in an engineering block diagram as follows. So we have a summing block with the external force coming in and the stiffness, the force from the spring being subtracted and the force from the damper being subtracted. So the resultant force is then applied to the mass, and what we get out then is acceleration. If we then integrate the acceleration, we get velocity. If we integrate the velocity, we get displacement. We need the displacement to be multiplied by the spring stiffness K to give us the stiffness force, and we need the velocity to be multiplied by the damping coefficient to give us the damping force. And so there's a block diagram that represents this equation of motion of the system. And so our job is going to be to convert this into basically a one-for-one model in Easy5 using standard Easy5 components. So on the next slide, I'm going to just show you the Easy5 screen, and I'm going to explain to you what we're going to do. We're going to effectively start by reproducing this diagram, this block diagram in Easy5. That's up here in the orange. When we've done that, we're going to move on and we're going to model the system using a transfer function and compare the answers. We're then going to use the Easy5 library component for a spring mass damper system and compare the answers, and then finally we're going to include the co-simulation link with Adams and compare the answers. So it's time then to move over to Easy5. So let me just bring the Easy5 user interface up, and there you have Easy5. If you've never opened up Easy5 before, let me just explain it to you. What we have here is called the canvas. This allows us to zoom in and zoom out on our model. All I've done is I've just imported an image, the image of the system that I want to model, so that it's right there before us and we can keep it on the canvas as we start to create the system. On the left here we have the library components, and so just to explain that Easy5 contains a number of libraries. There's the general purpose library, the aerospace library, electrical systems, gas dynamics, etc. The two that we're going to make use of most today is the general purpose library and the interactive simulation library. We also will make use of the extension library later to connect to Adams. But most of the time will be spent in the general purpose library. And then in the general purpose library, there's a whole host of groups of components, transfer functions, simple mathematical operators, integrators, controllers, function generators, and many others. I'd encourage you to kind of just browse through them. And if you want to know very quickly what a component does, a simple way to do that is to simply click down here on Auto Info. And then as you click on a block, it immediately brings up the help, which tells you what this block does. It gives you a little bit of information, and it gives you information on the parameters. If I now click another block, because auto info is ticked, immediately the description changes. And so you can very quickly just work your way through all the different components and see exactly what it is that each component does. I'm going to take that away for a moment. Well, before I do that, let me just give you one other tip here with regards to finding out what actually is available in Easy5, because that's helpful up front. And so what you can do is just go down and view the general purpose library documentation. If you do that, a window will pop up. So what you can see here is the alphabetical list of all the components in the general purpose library. And if you click on any one of them, let's just go to the divider, for example, you get the information. But you can also sort the list by the way the components are grouped in the Easy5 user interface. So there's all the transfer functions, there's all the discrete functions, and so on. And so this is a way in which you can very quickly see the entire list of components that are available to you, an extensive list of mathematical modeling tools that are in the general purpose library. So let's start, and what we're going to do now is we really want to just reproduce this block diagram on the canvas. And so let's start with the step function, and the step function we find in the function generators tab. And so obviously, being new to Easy5, you might have to look around a little bit to find things, but you soon will figure out where the components lie logically, and you'll be able to find them quite quickly. So we click on the step function block, and we simply just place it on the canvas. Now let me show you with the step function block what happens, and this is consistent then with all the blocks that you will use in Easy5. Once you've placed it on the canvas, if you double click the component, it brings up what is called the component data table. Now this has a number of tabs, and go to the first tab, and here you find the documentation related to this. So it is a step generator. The step is triggered at time equals to the T0 parameter, and it steps up to a value of the STP value. And so these labels you'll see correspond to the input tab. So T0 is the time at which the step function starts. And then here you have the value to which it steps up. What Easy5 does is any defaults are left at 0.9999. That's just to help you see that this is a value that is currently just using the block default. Basically, it's 1. So if you leave the default, it's going to generate a 1. But it's left in this format to show you that it's a value that you haven't changed. So we're going to say, right, we want to put 1 in there. And after 1 second, we want to step up our step function to a value of 20. This is unitless because we haven't connected it to anything, so we're not worrying about units in the step function block at this stage. Then we need a summing block. So we go now to our sum, multiply, and divide category, and there's various options. I'm going to take this one. And you'll see that we need 3 inputs. We need the external force, we need the force coming from the spring, and the force coming from the damper. So if we double click on the on the summing block, we can say, right, we want 3 inputs. And so that will introduce a third input on the top. And then if we go to the input tab, we now can decide how these values are going to be added or subtracted. And so input number 1 is going to be a positive, and the other 2 inputs both need to be negative. And so if we say minus minus, you'll see now we've got a -1 coming in here and a -1 coming in here. So that means we'll be subtracting inputs 2 and 3 from input number 1. The output of this block is then going to connect to the mathematical blocks of a divider and an integrator. A helpful thing to do with Easy5 is, as you are creating the blocks, is to change the labels to make a bit more sense. And so particularly the inputs are not so much of a problem, but the outputs are. Now you'll see we've got an input tab, a state tab, and a variables tab. Inputs are inputs to the system. States are internally calculated variables that are normally used by the component, and variables are normally the outputs of the component to the next block. And so in our case, the output of the step function is going to be our external force. So let's call it that, force external. And so now when we connect this block to this block, we see the F external is passed from the step function generator into the summing block. We're now going to add the divider. So let's go, and here's the divider under the sum, multiply, and divide. It's a simple divider block, and we want to specify that the output of the sum of the forces must be multiplied by the numerator, and that must be divided by the mass. So let's connect it. So we click the summing block, we click the divider. Now Easy5 pops this up automatically and says, I don't know what exactly you want to connect to what. And so we simply say, I want to connect the output of the summing junction to the numerator of this divider. I could pick either the numerator or the denominator. So suddenly I see the S out of my summing junction goes to the top of my divider block. Now, that's not a very helpful name, so I'm going to just double click on this, go to variables, and call this F resultant. So F resultant now is my numerator, and my denominator needs to be the mass. Now, I can simply go to inputs and change the denominator's value to 50. And there we have the first block modeled. But I want to do something a little bit extra here to just show you one of the nice capabilities of Easy5. And so I'm going to go to the special purpose tab here. And here's an option called the parameter value. And this allows me to actually create a variable. So I'm going to call this variable mass. And let me just call this mass variable. And the actual value, the parameter, is going to be called mass, and I'm going to make it 50. The benefit of doing this is that whenever I need to reference the mass in any block, instead of using the value 50 and going and finding all the blocks that make reference to the mass, I can simply make reference to this variable, and if I change the variable, it will update all the blocks that make use of the mass. And the way I do that is simply to go here now, and instead of putting 50 in there, I just say equals, and I use the @ annotation mass. And so if I do that, it turns green, showing me that it's a valid function, and it shows me the value that it's pulled from the mass variable. And so now, if I change the mass to 30 or to 40, it will automatically update this block. Right, so we've now got the force resultant being applied to the mass, and so what we get out of this block is the acceleration. So let's just change the variable then to say that the output of this divider is then the mass acceleration. So the mass acceleration comes out. We now need to integrate that so that we can integrate the acceleration to get a velocity. And so here's the integrator block. We're going to need two of those, one to integrate from acceleration to velocity, and another one to integrate from velocity to displacement. And so we can now connect the acceleration to this integrator, and what's coming out of this one in the states, what's being calculated internally then is the mass velocity. And so we connect that to this one, and so the mass velocity then goes into this integrator, and what's going to come out of this integrator is going to be the mass displacement. All right, so we've gone down the middle line. Now we need to be able to tap off the displacement and multiply it by the spring constant. So that's simply using a gain or multiplication block. And so we put this gain block up here for the spring, and we'll put a gain block down here for the damper. The gain block's pointing in the wrong direction right now, so we simply double click it, go to the configuration, and we can flip it. And we'll do that with both. So we flip the block so that they're pointing in the right direction. And we can now go and give it a meaningful name. So this one we'll call spring constant. And we go to the input tab and we say the gain value is 150 newtons per meter. And then this one we'll call the damping coefficient, and we give it a value of 20. Right, so at this stage they're not connected yet. So what I do is I click this integrator and I click the spring constant, and now I see that the displacement is now being applied to this. And so what comes out of this is then going to be the displacement times the spring constant is going to give me my spring force. So let me just label that correctly. So I'm going to say this is called F spring, and then I can connect F spring to my summing junction. And then I do the same at the bottom, but now I need the velocity. Now, all I do is I click on the velocity because it's already coming out this block, and then I click on my damping coefficient, and now you can see it branches the velocity value down to my damping coefficient, and what comes out of this is going to be F damper. And I can connect that into my summing block. And there we have the model complete. We've got a step function, and it gets fed into the equations of motion, and we should be able to model the dynamic response of the system. But we want to be able to see something while the simulation is running. Obviously, this runs very quickly, but just to show you what can be done, we're going to go to the interactive simulation library, and we're going to just pull out a strip chart. So we're just going to pull out a strip chart and put it over there. And what we want is the mass, the displacement. So we click the displacement leg, click the strip chart, and there it branches off into my strip chart. Just to show you as well, if I want to move the place where something is connected, I can select the branch and then come here to where it begins and just drag it, and you can move it anywhere to these little red triangles. So I'm going to move it to there, and then I can do the same with this one, move it around to there, and so I'm more happy with that. So let's start a simulation. So here we just open the current analysis block, and we tell it we want it to run for 30 seconds. Give it a time step very similar to with Adams. You give it a start time, a stop time, and your solver increment. And this is really the time step at which you're going to get outputs. And we press run. And the strip chart should pop up on the fly. What you'll see down at the bottom is it's now building the executable. So it now compiles this into a runtime executable. And then it runs the simulation. And there's the strip chart that's popped up, and you can see the dynamic response for the last 10 seconds. When the simulation is finished, Easy5 automatically will open the Easy5 plotter window, and it's busy coming up on my other monitor. So there it is. I'm going to bring it across. And because I haven't told it what I want to plot, I simply get all the available outputs of all the components available to plot. So there's the force in the damper. There's the external force. That makes sense. After 1 second, it switches up to 20 newtons and stays 20 newtons. Here's the resultant force that comes out of that summing block. There's the force of the spring. And then there's the displacement. So we can see that the block is stationary, and then it responds dynamically as an underdamped system to the input force. The acceleration's there, the velocity's there, as well as some other values that are generated by the system. So if we go and have a look, now you might say, well, how do I know if this is exactly the same as Adams? So let me show you that. And a simple way to do that, I'm going to just close this, is to go in the Easy5 simulation window here to plotting, and you can export the data as an external result file, which is in Adams format. So you say yes. So what that means now is when I rerun the simulation, it's also going to generate an Adams result file. And that will allow you to then actually import the results into your Adams model and compare the two. And since most of you are probably Adams users, we'll do it that way first. So we've run the simulation again. So what we're going to do now, there the plotting window comes up. So I'm going to just switch over to Adams, and as I switch over to Adams, we've run the same simulation in this model, or we didn't. Let's go and do that first. So let's just go and change the force to be exactly what we had in Easy5, which is effectively just a single step function that after 1 second steps from 0 up to 20. And I'm going to make it step very quickly. So I'm going to say in 0.1 of a second, it goes from 0 to 20. So we say OK, and we run the simulation. Okay, Adams is quite slow because the measure window is open, so I'm going to just close this for now so that it just speeds up a bit. All right, so we go across to the Adams post processor, and here we can go to our last run, and we can look at the displacement of the mass, and we get the Adams simulation results. We can now go and import results file and simply select the simulation that we've just run in Easy5, and we can import that. And now you'll see we have an extra result file here which contains the Easy5 requests, and there's the mass displacement over there. We add it, and we see that the Adams run and the Easy5 modeling of the equations of motion give you the exact same response. And so you can be very grateful that your Adams models over the years are accurate, because now you've done it by hand using the equations of motion in Easy5, and you can see that the results are identical. All right, so let's return back to our presentation and move on to the next step. So the next step is to now move on and model, instead of the detailed equations of motion in the time domain, we want to now model a transfer function, which is a single block that represents everything that's in the orange block. Now, a transfer function basically represents the dynamics of the system in the frequency domain, or the S domain. Essentially, a transfer function is the ratio of the output of the system, x, capital X as a function of S, due to the input, capital F as a function of S in the frequency domain. And so the way we get from the time-based equations of motion to the frequency domain is by obtaining the Laplace transformation of the equations of motion. Now, this is commonly used, as I mentioned in the introduction, in electronic engineering, and it's the standard approach used mainly by control system engineers when they design control systems. So what we have here is we have the original equation of motion in the time domain, and by doing the Laplace transformation, we're able to get the ratio, which is effectively the transfer function of the output of the system x to the input of the system in the frequency domain. If you want to see the detailed steps of how to go about doing that, there's a great video here at xengineer.org on the steps to get from this to this, and I would encourage you to watch that. Now, when we move across to Easy5, we've got a simple transfer function component. There are actually numerous transfer function blocks in Easy5, and they all follow the same convention as shown over here. The only quirk is that the constant in front of the first or the highest order term in Easy5 must be 1. So for the given transfer function of our mass spring damper system, we came up with this equation: 1 over mass times s squared plus the damping coefficient times s plus k. But we need to have 1 in front of the s squared component. And so we have to multiply all of the terms by 1 over m in order to cancel this out. And so that effectively gives us this. The top one becomes 1 over m. M cancels out over here, and then we get the damping coefficient divided by the mass, and we get the stiffness coefficient divided by the mass. So this is the form that we're going to use in our transfer function in Easy5. So let's move over and do that. So I'm going to leave this model there. Let me just do what I did in my diagram. I'm going to just add an outline, basically just drag this orange block there to show that this is the first way that we've modeled our system. And now we're going to add a transfer function. So we go back to our general purpose library. We go to the transfer function group, and we go down to this general transfer function over here. There are various different ones for different applications, and you can go and read the documentation, but this is the most general one. And we now need to effectively put in the coefficients required. And so we simply double click on it, and we now need to just basically fill in the coefficients of each of the components in our transfer function. So in our case, we've simply got Z0 is 1 over M. And so what we can do here is we just simply say Z0 is equal to 1 divided by at mass. And Z1 in our case is 0, so we make that 0. And if we look at the the denominator coefficients, we know that S squared has a value of 1. We don't need to fill that in. P0 is the last one. That was K over M. So we'll say is equal to K was 150 divided by at mass. And P1 is the damping. And so that's equals to 20 divided by at mass. And there we have the transfer function for our specific system. And it's as simple as that. We can now take the same external disturbance force and connect it to our transfer function as an input. And we take our transfer function and we connect it to our strip chart as an output. And if we've done everything correctly, then this block should give us exactly the same response as being calculated in the frequency domain as we would have got having done the equations of motion in the time domain. Let's just specify the output with a variable name that is simple. So we're going to call this transfer function mass displacement to distinguish it from the mass displacement over there. All right, so if we run the simulation now, we should see two graphs in our strip chart. It's compiling, it begins the analysis execution, and hopefully we'll see the strip chart pop up. There we do. And already you can see two graphs, and they are giving exactly the same results. One graph being plotted identically on top of the other. And so it does make sense. And you can certainly see why, from a control system perspective, it's far simpler to include the dynamics of the system modeled as a single transfer function, as opposed to trying to break down the equations of motion and modeling them as we've done in the first place. And so now what we want to be able to compare is mass displacement with transfer function mass displacement. And simply as I click on these, you can see the graph changes, but the graph is identical. But what I want to show you is just one or two things about the post-processor here. The graphing post-processor is very powerful. We've currently got the mass displacement graph selected. Simply by holding down Control on the keyboard and dragging my mouse, we get a coordinate window, which then plots the exact value for you on the window. So you can very accurately track the value of your results using the Control key. But what we can also do here is we can select the graph, right click, and then say add a new curve. And what I'm going to now do is I'm going to add, sorry, this window's popped up over there. There we go. I'm going to add now the transfer function mass. And I want it to be let's say blue line. It's quite thick, and I want it to be dashed. And so now this is just tracking my value. If I zoom in over here, I can see that the two graphs follow each other exactly. All right, so that's good news. It means our equations of motion and our transfer function are doing what they are meant to do. Once you've done anything, and this is a little data tag, let me show you how you do that. You simply right click and you just say add a data tag to a graph, and you can click on this and edit the data tag properties, which just the text, for example, we can say is large, and this data tag will now be saved in what's called a layout file. So we've now done a couple things. We've changed colors of the graph, we've added some data points, we've plotted two graphs on the same set of axes. This can all be saved in what's called a layout file. So when I exit now by closing this, Easy5 says, do you want to save the changes to the layout file? And I say save. The good news now is that if I run the simulation, let's say for 20 seconds, using a different time step, and I run the simulation, it repeats the calculations. And when I go over to the plotting window, so I'm going to just let this finish. It's running a bit slower because I've set the time step smaller. Now the Easy5 plotter will open up, and I don't have to go and redo anything that I've done previously. What I get by default is the standard results. But if I click on the layout file, I now get all the things that I've previously saved. The colors, the thicknesses, the data tags, etc., the two graphs on the same axes. So the great thing is here, you can do this, you put a lot of effort into your graphs, and then as you run multiple simulations, you simply click on the selected layout file, and all those settings are immediately applied to the latest set of results that Easy5 has generated. All right, so we've done two approaches. So let me just drag another component, another outline around this guy. I'm going to, edit this, properties, make it, let's call it cyan, and simply just drag this around my transfer function. Okay, so we've got the orange block was the equations of motion, the cyan block is the transfer function, and we saw the results are identical. Now that's a lot of maths, a lot of hard work, and obviously error prone, and so ideally we want to find a better way to do that, and Easy5 certainly gives us that. And so one of the libraries that contains the ability to model various mechanical components and systems is the gas dynamics library. And so if I go to the gas dynamics library, I can see I've got actuators and chemical reactors and heat exchangers and all kinds of things typical to a gas dynamic system. But one of them is body dynamics. And there we see immediately the single mass spring damper system with hard limits and friction. So that sounds interesting already. There are others, two mass systems, moving frame systems. This is kind of three masses. We're going to just take this component and put it here. Okay, so before we add the Easy5 a single mass component, let me just explain to you how this works. So Easy5 has a whole host of what we call engineering components. Both the previous methods, as I mentioned, required you to derive the mathematical equations, either in the time or the frequency domain. Obviously, there's room there for error, and if there is an error there, it's difficult to debug. So the real power of Easy5 lies in its libraries and the libraries of engineering components. And so these blocks contain all the mathematical equations necessary to model the system using physical engineering inputs as opposed to mathematical equation inputs. And so these blocks not only model the basic maths quite simply, but they also include much more advanced non-linear features, things like friction and bump stops. And so here you can see some examples of various spring mass damper configurations that Easy5 has standard, other types of components, fans, compressors, gearboxes, shafts, rotational inertias, clutches, and so the lists go on. I'd encourage you to explore those. Now, what's great with each of these engineering components is that when you double click one of them on the canvas and you click on the documentation or configuration tab, firstly, you're going to get some very helpful documentation that explains what the system does, how they've modeled it, what physics it includes and doesn't include. There's also some options down here to set various options for that given component. And then if you click on the Inputs tab, you'll be presented with the engineering input that is required by this component. For example, the Coulomb friction force, the linear damping coefficient, the mass of the block or the displacement of the block that's allowed, etc. And so it's all presented in normal engineering terminology as you would be familiar with coming from Adams. So let's move over to Easy5 and add that simple mass spring damper component to the model. A little caveat: if you use anything in the gas dynamics library, you have to include under miscellaneous. You have to include the gas properties. We don't use the gas properties in any other components. I'm not even going to bother about going into the gas properties component. But obviously, if you were modeling a real gas dynamic system, you need to specify which gas and what temperature and things like that. But in order for this component to work, it will need just the gas properties box, a block dropped onto the canvas. So we can now connect our input force to our single mass component. Now what you'll see is I'm prompted with what I want to connect my force to, and so I can see there's a whole bunch of options, and here's the external force. So that makes sense. My applied force gets applied to the external force in this component. If I double click on this, you'll see that I am presented with the documentation, and this is quite comprehensive. It shows you how the system is modeled with a spring and a damper, what the minimum and maximum positions are, what forces are being applied, how and where friction is being applied to the system. And so I can also set up certain configurations. I can say, right, I've got my damper is being modeled with a damping coefficient or a damping ratio. So we've used a damping coefficient in Adams, so let's stick with that. And then when I later want to introduce friction, how do I want to include friction as an exact formulation or smooth? So we're going to leave it on exact for now because we're going to ignore friction to start off with. So if I move to the Inputs tab, now you'll see that I'm simply presented with engineering inputs. Here's the maximum allowable displacement of the center of gravity, 1e20 and minus 20, so effectively an infinite amount of movement is allowed. Here I can specify the mass of the body, and so in kilograms, and so I simply say equals again at mass. And then I can put the spring rate in, and the damping is under the friction parameters. There's the damping coefficient. Now, just one thing to note, and that is that the units are different. We've modeled on the Adams side in newtons and meters. This component is set up in the units of centimeters. And so we need to just convert the spring rate of 150 newtons per meter. So that will then be 1.5 newtons per centimeter. And then for the damping, instead of 20, it will be 0.2 Newton seconds per centimeter. So just keep that in mind, that when you are using the built-in libraries, you need to make sure that you are using the units in which these components were developed. And then if we go to the variables, we get the output displacement of the mass. And so let's just call this, we'll call this the Easy5 displacement, mass displacement. So we can distinguish it from the transfer function, and we can distinguish it from the original equation. The challenge we have now is that the output here, in terms of the mass displacement, is coming out in centimeters and not meters. So we could use a mathematical gain, but there is a nice little tool here which has got to do with the unit conversion. Let me just find it. There we go, the units converter. So we simply put down a units converter here, and we tell it that we're converting from, we want to convert to the output units from the standard gas dynamics outputs and length. So we can pick which unit we're wanting to do the conversion of. So we want to convert from centimeters to meters, and so here we then go that we want the output in meters. And that's it. So we put centimeters in there. So we're going to basically just connect the displacement. Our E5 mass displacement is going to be put out over there. So what we're going to do here is just change the name of this output to be E5 mass displacement meters, just to distinguish it from what's coming in, and that we can now just plug into our strip chart as well. So now we've got three different approaches to modeling the same system. Let's see if they all give the same results. And so let's just go back here to 30 seconds, 0.1, and we run the simulation. If we've done everything correctly, as the strip chart pops up, we should see three graphs all on top of each other. And there we have it. Three pretty much look to be identical on top of each other. So that's good news. That means that the equations of motion that we derived from first principles have been correctly translated into a transfer function, and that immediately ties up with what we find in this component. And so we've got our comparative graph here. Let's add another curve, add a new curve, and now we can pick the E5 mass displacement, and we can make it a magenta line, and so there we see all the lines exactly on top of each other, and so we know that we've been able to correctly model the system using three different approaches. All right, and so the last step in the first part of this video then is to add the Adams co-simulation. And so what I'm going to do now is move down to my extensions, and I'm going to drag an Adams block onto the canvas. Now, we're going to have to go to Adams and do a bit of work first before we can connect Adams to Easy5. All right, so the last approach that we're going to take is to actually include the Adams component. And so what this does is this Adams component effectively is a direct live co-simulation link to Adams. And so when you run this component, it'll fire up Adams in the background. Easy5 will take the force value that you've applied to the model. It'll pass it across to Adams. Adams will then apply that force to the Adams model and will send the parameters back that you are interested in, the velocity, the displacements, the accelerations. You can specify whatever inputs and outputs you want in your Adams model. And effectively, Easy5 controls the simulation. It sets the time stepping, and for each time step in Easy5, it will pass the information to Adams. Adams will calculate the dynamics and then send the response back. And so this allows us to then actually couple Easy5 with our detailed 3D Adams model. So let's do that quickly, and this will be the last step in this video. So we bring up our Adams model, and the first thing we're going to need to do, obviously, is to change the force, because the force now needs to be controlled by Easy5. Now, for us to pass parameters backwards and forwards between Easy5 and Adams, we need to create a couple of state variables in Adams. And so we go here to the Elements tab in Adams, and it's this little X icon creates a state variable. And simply a state variable is simply a function or a variable that either Easy5 will overwrite or that Adams will calculate in order to pass it back to Easy5. And so if I close that and I open up my system elements here, you'll see that I've created 6 state variables. Let's start with the external force. I've created one called F external. And you'll see that the value is simply 0. That's because Adams is, this value 0 is going to be overridden in Adams by Easy5 for each time step. The others are all calculations that Adams is doing and passing values back to Easy5. Now, all we really need to pass back to Easy5 is the displacement, the mass displacement, because that's what we're using to compare our models. But there's no harm in passing more parameters back to Easy5, and the benefit of that is that you can then plot these Adams variables in the Easy5 plotter in order to compare certain quantities to make sure that they are the same. But really all we need for our model is a force coming in and a displacement going back. The rest is optional. And to send the displacement back, we simply say dx of mass cm. This is using standard Adams function language. So that's what we're going to pass back to Easy5. Once we've done that, we need to go and edit the force now and tell the force not to have a static value or a step function, but to actually make use of a variable. And so we go here to data element, algebraic variable value. You can press assist, right click, and guess the force external. All right, if you're familiar with this, so now we get a varval of F external. So this is now the value that's being applied to the force, and this value is going to be overwritten each time step by Easy5. And so that way now this force is basically connected to Easy5. And so we have to then go to the plugin tab, to the controls plugin, and I go to plant export, and I select a new controls plant export, and I'm going to call this mass spring damper Easy5 COSM, and the file prefix I'm going to just make use of the same. I don't want it to do an initial static analysis, and now I simply say, well, what are the input signals to my Adams model? And I can right click and I can select that state variable called F external, and then my outputs back to Adams, back to Easy5 is going to be the mass dx. That's it. That's all we need. One input, one output. We're using Easy5. You can obviously do the same with MATLAB Simulink, or the new sort of standard, which is the functional mockup standard for communicating between solvers, but we're going to use Easy5. We want to do a full nonlinear analysis using the C++ solver, and that's it. Now, when we say OK, Adams will now write a bunch of files into the folder in which this model is written, and that needs to be the same folder in which your Easy5 model is as well. So we're going to switch now to Easy5. And we now double click on the Adams component. And the first thing we have to do, and you only have to do this once, is we have to say select or configure the Adams model. When I do that, it brings up a window and it looks in the file, in the folder, and it finds any co-simulation plant models that have been written. This is the one we've just written out. we want to run it in full co-simulation mode, and so we say done. Once we've done that, you'll see very quickly it pops up with the information it found. And it shows us that if external is a user-defined input, and it gives us various options. We want it to run with Adams in animation mode. 0 is animation off, means it simply runs the Adams solver in the background. It's very fast and efficient, but you can't see what's happening. 1 will actually fire up Adams view so that you can watch the animation while it's running. We don't want any static analysis. Here we set the output interval to be the same as the as the Easy5 time step, so that Adams and Easy5 are running at the same time steps. You can pick different time steps. You then just have to make use of interpolation. I anyway like to just switch this on, that if Adams and Easy5 are slightly out in terms of time stepping, that it will interpolate from the one time step to the next. It makes it, it uses linear interpolation, which gives you just a more accurate result. All right, and so that's all we need to kind of just configure the component. What we can now do is we can take our external force and we can connect it here. We say this F external is going to connect to this F external, and we're going to have a problem with that just now because Easy5 doesn't like variables to have the same names, but let's wait and see how it warns us. And then we take the output from the Adams model and we plug it into our strip chart, and so it's the mass from Adams must go to the fourth input on our strip chart. And we've got two problems. So no, the mass dx is great. We've got mass displacement, transfer mass displacement, Easy5 mass displacement, and here we've got mass dx. I'm going to try and run it and let's see what happens. And I think it's going to give me an error now because of those variable names that are the same. Okay, it's happy. Yeah, I think that's simply because the one is coming from Adams. Now, what should happen is we should see the Adams view window appear. It's busy firing up on my other monitor, so I'll bring it across in a second. So Easy5 is starting up Adams in the background. There it is. Let's bring it across. Okay, so there's Adams. It's just fired up. It's busy loading the Adams model, and the simulation is now starting to run. And so you've got Easy5 running 4 simulations, 3 are calculating itself, and the fourth one is actually being calculated by Adams, and the values are being passed back to Easy5. Just running on a not a great laptop here and without great graphics, but we've got the strip chart obviously updating, and we've got the communication happening between Adams and Easy5. So it's a little bit slower due to the graphics updating that's taking place. But what we can see already at face value, without examining it in detail, is that from an engineering perspective, our Adams co-simulation model is giving exactly the same results as all the previous methods that we had applied in Easy5. If I want to stop the simulation, I stop it on the Easy5 side, and that will automatically close down Adams, wrap up the simulation, and then present us with the results from that co-simulation run. And so let's just start with our previous graph that had the 3 results, and let's add now to that another new curve, which is going to be, in this case, mass dx. That's the one that comes from Adams, and we're going to make that, let's call it cyan. Let's make it a little bit thicker so we can see. Now, at a distance, it looks essentially the same. What you will notice, however, is that if we zoom in, we're going to see some slight discrepancies. And that partially has to do with the way in which the Adams run is always going to be slightly out of sync with the Easy5 run, because Easy5 has to first run a step before it passes information through to Adams, and vice versa. But for all practical purposes, we can see that the answers in terms of the peak values are identical, and as you would expect, the system is tracking the other mathematical models perfectly. All right, so that brings us to the end of this getting started guide. The next video, we will then introduce nonlinearities, friction, and bump stops into the model. We'll use both the single mass component to do that, as well as the Adams component. And so that'll be the next step in the model, will be to do friction and bump stops. Hope you'll join us for the next video.